Welcome to the webinar for NASA Langley Research Center's Floating Ultrasonic Transducer. We greatly appreciate your attendance at today's event. I'm Andy Helminger, and I support the Technology Transfer Program at NASA Langley. As part of NASA's mission, the Technology Transfer Program helps connect U.S. companies with new technologies developed by NASA researchers for the space program. And the ultimate goal is to commercialize these NASA-developed technologies. The floating ultrasonic transducer is one of these new technologies, and we're very excited to tell you about it today. But before we get started, a few housekeeping details. If you have questions during the feature presentation today, please type them into the chat box at the left-hand side of your screen. And at the end of the talk, I'll be back to pose some of those questions to our NASA speaker. We'll try to fit in as many questions as we have time to answer today. But if we don't get to your question in this session, please contact us afterwards. You'll find a web link on the last slide of this presentation where you can reach us. And now I'd like to introduce our featured speaker, Joe Zalameda. Joe is a co-inventor of NASA's Floating Ultrasonic Transducer. Joe works in the Non-Destructive Evaluation Sciences branch at NASA Langley. His areas of research are in thermal, non-destructive evaluation, and sensors development. Joe?
Okay, thanks, Andy, and thanks for everybody signing in today. Let's go to the next slide here. I'll be presenting basically an introduction to the motivation behind developing this technology, and the technology is applied for inspection of composite structures. And I'll talk about, and I'll do an introduction in terms of some of the other commonly used ultrasonic inspection techniques out there, but I won't spend too much time on that. And then I'll talk about, well, we're currently using a non-emergent ultrasonic setup, and I'll talk about the disadvantages of that and why we went to this dry coupling concept. So anyway, I'll have a little short video, and then after the video, talk more in detail about the system. I'll present some early results and comparison to water tank scan, and then I'll finish with some future plans of this for this technology. Okay, so currently for ultrasonic inspections, the most popular method used is a water tank scan. And you can see in the upper left image, we have a water tank. And so water is used as a couplant between the transducer to couple the energy from the transducer to the sample that you're inspecting. So the object that you're inspecting has to be totally immersed in the water tank. And the disadvantage of that, of course, is that if you have a really big object that you want to inspect, it might not fit in the water tank. So basically, what some people do is a point measurement where they'll you can see in the middle top image, you can see the operator has a transducer, he's applying fingertip pressure, and he's going to move that transducer over an area, apply pressure, and do a measurement. Okay, so to make things easier, there's been some development of a wheel transducer, and so that technology is like a roller that can roll on the surface to cover the area to do the inspection. So you have to apply pressure, and because it's on an axle, you can only go in one direction. And you can see in the lower left image that you have a hand scan assembly, which is an ultrasonic wheel transducer and a frame. And so it can only go in one direction, and you can see in that lower left image there's some vertical lines that are drawn, so the inspector will push that assembly and following that vertical line to build up the inspection image. Some other techniques out there is a water squirter jet system, and so these systems are commonly seen in industry. Again, water is the medium used to couple the ultrasonic energy to inspect the structure, and this is applied for large structures. With this water squirter jet system, you have to have a water containment system, so the water has to be collected, and then either it's recycled and filtered or it's just drained out, but it makes it more complicated having to use the water squirter jet system. On the top right system, you have a dripless bubbler system, kind of the same technology or technique where you're using water as a couplant. But in this case here, what they're doing is they're pumping water in on the right side into a column, and then they're pumping the water out with a vacuum on the other side. So there is some water leakage there, so there might be some water containment issues, but it's just another way this technology performs the inspection using ultrasound. Another technique is air-coupled ultrasound, where now air is the medium that is used to couple the ultrasonic energy from the transducer to the sample. And in this case here, because air is such a poor impedance match, between the transducer and the sample. You have to go to really high powers. Also, you have to go to lower frequencies, and if you go to lower frequencies, then you have longer wavelengths. And so, therefore, if you have longer wavelengths, your resolution of your inspection is not as good. Okay, so NASA uses ultrasonic inspection technologies, and requirements are for rapid quantitative through thickness inspection of advanced composite structures. And so if you see in the right image there, you have an ultrasonic inspection. The good thing about ultrasonics is it gives you the assessment of the damage as a function of depth. And so it's commonly used for inspecting manufactured parts or parts in service. For our particular application, for materials research, there's a need to develop systems for inspection of composite parts during load testing. So you have a part on a load frame, and we apply a load to it, and then we want to, after a certain amount of load that is applied, we want to perform the inspection. So we want to leave the part on the load frame. Okay, let me go to the next slide. Okay, so how we've addressed that is currently we're using a non-emergent ultrasonic scan for the in-situ inspection of composite structures. And this technology uses a trapped water column with a flexible membrane tip. It's actually like a water balloon on the end of the column there. And what that does is that couples the ultrasonic energy through the transducer, through a water column, and into this like a water balloon almost. And here you can see this technology is applied for the in-situ inspection of composite structures that are on a load frame. The advantages of being able to do the inspection while on the load frame instead of taking it down and putting it in a water tank or X-ray CT scanner is number one, you're going to save time if you can do the inspection in situ. Just leave the structure. You don't have to unbolt it and then rebolt it back onto the test frame. Make sure your torque of your bolts are correct. The second advantage is if you have some damage that you've grown, you don't want to grow it additionally by handling the structure, by taking it off and moving it. You want all the damage to be associated with the amount of loading that's been applied to that structure. And this technology, this assessment, to be able to calibrate and develop their models to predict the extent of damage based on fatigue loading. Okay, so the disadvantage of this current setup is that you have to, even though you have this water balloon tip on the end of this measurement system, you have to apply water to the surface. So normally what's happening is you have an operator that's squirting water on the surface. The water has to be sprayed evenly on the surface to get consistent results. If the water is not sprayed evenly, then the scan will have to be redone. Sometimes you have to have two operators to do this, one who's spraying the water. The other person is watching the signal on a computer screen and making sure that the signals are uniform and that you don't have to redo the scan. Okay, the water containment that we do, when the water, since it's a vertical surface, the water drips down. We use some paper towels at the bottom, but still the area can be contaminated. And as you can see in this right image here, we have some rust that is formed on the test sample. Okay, so what we've devised is a dry coupling ultrasonic technique. And this technique is based on a momentary touching scheme where the ultrasonic transducer is vibrated on the surface. So the vibration does two things. Number one, when the vibration applies a small force that enables coupling of the ultrasonic energy from the transducer to the part that you're inspecting. And since the ultrasonic energy, the velocities are very fast, on the order of hundreds of microseconds, you only have to touch it for a very short amount of time in order to perform the inspection. Okay, the other thing it does with this momentary touching scheme is it facilitates or allows you to move the transducer across the surface. And so that's the two benefits of that. It's very simple idea. Now the transducer has a small coupling layer, a dry coupling layer between the transducer and the structure that you're inspecting. And so when a small amount of pressure is applied, that's when the ultrasonic energy is able to couple in and perform the inspection. So with this technique, no external couplants are required, no gel or water couplants are required, and we feel like this makes the ultrasonic inspection more practical. So we'll show a short video here that will demonstrate this technology.
Hi, let me demonstrate this technology to you. I have an ultrasonic transducer here, and I have a sample that I want to inspect here. So if I don't have any coupling medium, I push down on the sample, and you can see here on the screen that there's no change in the ultrasonic waveform. So a commonly used medium is water. So I'll just put a little water on the surface. And as you can see, as I press down, you can see the waveform change, showing that the ultrasonic energy is transferring into the sample and it's reflecting back through the sample. Now this sample here has a defect. As you can see here, that the waveform changes. Now this area here is where there's no defect, but you can see the ultrasonic energy is coupled into the sample. And as we move the transducer over an area where there's a defect, we can see here that we get a difference in the ultrasonic waveform response. So I'll go ahead and dry off the sample in the transducer, and I'll demonstrate the solid couplant material. It's nitrile rubber on the surface of the sample, and then I'll place the transducer on the membrane. There again is a signal where there's no defect, and then if I move the transducer up, you can see that the peaks are closer together. You get the multiple echoes because there's a delamination at the midplane of the sample. Okay, so now what we've done here is that I have a transducer where we've now taken the solid couplant membrane, the nitrile rubber, and we placed it over the transducer. And it just requires slight fingertip pressure to help transmit the energy into the composite part. Okay, so that's no defect, and then defect there. Now I want to demonstrate this technology on a pipe with material loss inside, so that to simulate corrosion damage in the pipe. So if we take the transducer and solid couplant material and apply it in an area where there's no defect, you can see again the multiple echoes and the ring down effect. Notice the spacing. If I move the transducer over an area where there's a defect, you can see again the multiple echoes, but they're spaced closer together. One possible benefit of using the solid couplant membrane is if you have a rough surface that you have to inspect, you can go to thicker membranes. So you can lay that over the sample. You can either lay it over the sample or have it on the transducer, and then the thickness of the membrane will account for the surface roughness, so you can still do your inspection over an area that's rough. So now we have the transducer with the solid couplant membrane mounted to a voice coil motor, and what that does is applies slight pressure, okay, because it has a magnet in the coil. It can move. As I send electrical current to the motor, it can move this up and down. And as you can see on the screen here, as I slightly push down, you can see the waveform here, this signal here, which is the back surface of the composite sample that I'm inspecting. So now I'll apply an electrical signal to the linear voice coil motor, and that will produce the signal that was shown previously, but instead of applying fingertip pressure, now we are modulating the transducer assembly electromechanically, and that's shown here. So we're getting ultrasonic coupling to the transducer solid membrane. Because it's vibrating on the surface, we can move the transducer and still get the inspection. So right now we're vibrating the transducer on the surface, and we can scan it to make multiple measurements on the surface. And the vibration allows the transducer to move on the surface, or in effect float on the surface. Okay, so here is some data that we took previously on the sample that we performed the previous scan on. This is time, and this is voltage for all the waveforms that we've acquired. And so we can step through in time by moving this time window through the data. So we have the near surface indentation here from the impact damage, And as we slide this through, we can go through in depth and measure the extent of the damage that should be larger than the indentation, the subsurface damage. So as I slide this window through the data, we will be inspecting deeper into the structure, and we can see subsurface damage showing up here. And as we slide it further, we can see the extent of the subsurface damage shown here.
Okay, so just show the overall system. Is a picture of the overall system shown here, and you've seen it in the video, so I'll just go to the next slide. And this is the overall system description here, and the thing I want to focus on is the timing electronics. So the timing electronics controls the actuator power supply. So the timing electronics allows the synchronization between how we move the transducer to when we send the ultrasonic signal and then receive the echo back. We also have a waveform digitizer to acquire our ultrasonic signals, and this is all controlled by a computer. The computer also controls the scanner electronics. Okay, so here's just a close-up description of the transducer and actuator. The transducer we're using is a 5 megahertz broadband unfocused transducer with a diameter of about 1/8 of an inch. The actuator diameter is about 3/4 of an inch and is about 1 1/4 inches in length. You'll see that there's a rod that sticks up from the actuator, and this is a linear bearing for normal displacement. So what this does is keeps the transducer normal to the surface of the part that we're inspecting. Okay, so the actuator can be precisely controlled by applying a voltage to the coil, and so we can get stroke displacements up to 0.5 inches, but for this application, all we need is small stroke displacements. And then as we're coupling the energy to the sample, we're only using fingertip pressure. The vibration frequencies of the actuator can be anywhere around 160 to 180 hertz, and the duty cycle of that is it doesn't have to be 50%, but it can be less than that, anywhere from 15% to 30% duty cycle. The voltage applied to the coil is about 2.5 volts, and that provides about 400 milliwatts of power to the actuator. So here's a close-up of the transducer with the solid membrane. The solid membrane that we're using is nitrile rubber, about 16,000ths of an inch thick. One of the things that we do, we apply a small amount of gel couplant on the transducer face and the inner surface of the solid couplant. Okay, so what that does is helps our efficiency in transferring the ultrasonic energy into the solid couplant. The outside face of the solid couplant is completely dry. Okay, and obviously that we can apply the solid couplant to a single transducer or array of transducers or a phased array of transducers. So here's the timing diagram. If you'll look at the second waveform from the top, we have the actuator voltage. So that actuator voltage is supplied to the coil, the linear voice coil motor, and that coil then, with the magnet in the center of the coil, causes the vertical displacement. And so since you're controlling the transducer assembly electromechanically, there's going to be some delay in moving that mass down. So there's going to be a delay when you get the maximum contact pressure from when you apply the actuator voltage. And so we have a phase delay. We introduce a phase delay. So we're synchronizing the firing of the ultrasonic pulse and the acquisition of the ultrasonic pulse to that phase delay when we get maximum contact pressure. And we've measured it to be about 2 milliseconds. Again, it's just repeated again. So we modulate the frequency of or generate the frequency. The actuator frequency is about 160 to 180 hertz. We can go higher in frequency by using actuator with a larger magnet, with a stronger coil. We can increase that frequency. Okay, so this is just a plot showing a comparison when we have no activation to activation. So the top plot on the right, when you have no activation, is when you get no coupling of the ultrasonic energy into the part, and therefore you don't get any measurement of the back wall echo. When you have activation, then you're able to couple the ultrasonic energy into the part, and you're able to detect the back wall echo. And this is just a comparison of the two signals, the A-scan signals that you typically get. Okay, and this is a comparison with the detection of the defect. So with activation on both of these plots, activation where there's no defect, then you get the back wall echo. If you have a defect, in this case the composite has a defect mid-plane of the sample, then you get a reflection in the middle of the time between the front surface and the back wall echo. And that's shown in the lower plot there. You get a reflected signal that in half the time, and that's due to the delamination at the composite delamination located at the mid-plane. Okay, so with those results that we had previously, we wanted to compare a C-scan to a water tank scan. The C-scan's from a dry scan to a water tank scan. So if you look at the images shown on the right-hand side, the two images on the right-hand side is the water tank scan. That is kind of like the gold standard of ultrasonic inspection. Okay, and that was done with a higher resolution, about 451 by 181 pixels. This is using a focus transducer, I think about 10 megahertz, so it's focused on the surface. So that is our water tank scan. On the left two images is our dry scan technique, and this is at a lower resolution, about 218 by 76. This is using a 5 megahertz unfocused transducer. And you can see here that the results are fairly similar, and these results look very, very promising. And so you can see the images, these scans here are comparing a dry scan near surface to a water tank near surface scan, and you can see they're very similar. And also the mid-plane where that delamination is shows a delamination area very, very similar to the water tank scan. Okay, and so here's a comparison of the ultrasonic signals of the A scans at the same location, relatively the same locations, and you can see, just compare the two waveforms, and you can see that the pulse is shown where the damage is detected for the dry scan as compared to the water tank scan. Of course, we've used different ultrasonic transducers, and therefore the signals aren't going to be completely the same, but you can see that they're relatively in shape. They look like they have fairly good agreement. Okay, so the significance of this technology, it's a real simple concept of moving the transducer, this momentary touching technique, where the transducer is floating on the surface, benefits you in two ways. Number one, it benefits you in terms of the movement, allows you to couple the ultrasonic energy into the part, and also the vibration allows you to be able to move the transducer in any direction, X, Y, on the part. And because of this, you don't need any water or gel couplants. And we feel like because of this significantly simplifies the inspection, especially for vertical or overhead surfaces, and also makes it more practical because you don't need any water containment systems, or you don't need to apply water or gel and then have to clean it up afterwards. Okay, and so the applications of this include material inspections that cannot be contaminated. Again, the picture I showed previously of the rusted area of that composite part with the metal fixture attached to the composite part. Also, of course, we want to apply this technique to inspection of composite structures, in situ inspection of composite structures when they're fatigue loaded. We feel also there's a potential here for inspecting structures in space. Obviously, if you have a zero gravity environment, that you can't have any liquid couplants. Again, any parts that have special coatings that can't be contaminated, this technique might have potential for that, and also medical, where over the surface of the skin you don't have to put the gel couplant and then take the transducer and move it over an area. If you're inspecting a large area, then you need to potentially cover the entire area with gel couplant and then move that transducer over the area. The other point to make is that perhaps if you're vibrating the transducer, then perhaps you don't have to press down as much on the skin, and perhaps this might make the medical measurement more user-friendly in that respect. Okay, so the other thing is that you can look at surface roughnesses with this technique. If you go to a thicker layer, so the thicker solid couplant layer might account for the surface roughness, and so that has to be studied more in terms of, obviously, if you use a thicker layer, you're going to have more attenuation of your ultrasonic signals, so we have to study the trade-offs of that. Okay, so future plans, We feel that we want to be able to convert the mechanical scanning to a hand scanning, so now the ultrasonic transducers system is vibrating in your hand, and then you move the hand anywhere in XY location to build up your inspection image. One of the things I did not note in the previous slides is that we did not synchronize the movement of the scanning system with the actuator movement and also with the pulsing of the ultrasonic signals, of the ultrasonic measurements. I think that's going to be the next step. We feel like if we can do that, we can improve our repeatability of our A scans in this measurement technique. And so as we're able to synchronize the movement to the actuator movement, and that actuator movement is synchronized to when we fire the ultrasonic pulses and listen back for the echo, that will help make the measurement more efficient, improve our signal and noise, and improve our repeatability of our A scans. Okay, another thing that we can do is implement a delay line to improve the measured signal. This will allow us to perhaps focus the ultrasonic energy on the surface or anywhere you want within the thickness of the sample. It'll also allow us to, with the delay line, look at thinner structures. So if we're looking at a face sheet of a composite sandwich structure, that'll help us to look at those type structures. And again, I'll mention again that we want to study the effects of different thickness solid couplet membranes. Perhaps there might be another solid couplet material out there that's better than what we've used. And lastly, we want to be able to apply this technology for in situ inspection of fatigue-tested composite structures and publish the results in literature. So we're looking at about a year's time frame to when we can apply this technology for testing composite structures in load frames and to when we can present it at a conference.
All right. Thank you, Joe. We have several questions from our audience. The first question is, how did you pick the solid couplet membrane you're using for this device, and what other solid couplets did you consider?
Okay, that's a good question. So as I mentioned in previous slides, that we had this non-emergent technique using the water balloon on the end of the ultrasonic measurement system, and so that was nitrile rubber. So with that system, we tested some other water balloon membrane, and the nitrile rubber seemed to be the best one for that application. So naturally, we took that nitrile rubber and used it for the solid couplet application, and it seemed to work well. We've looked at some other rubbers, and there's also a product that we've looked at that's commercially available called Aqualine. We've looked at that material, and we could get it in different thicknesses, but they weren't quite as thin as we would want to use for our application. So we did purchase some of those. They work rather well, but we couldn't get it in the thinner thicknesses that we wanted. So basically, we're wanting to perhaps maybe look at some different materials. If there's better materials out there, we would like to look at that. But right now, the nitrile rubber seems to be the best that we've found so far.
All right, thank you, Joe. Our next question from the audience is, what is the best resolution you can get with the membrane in place? What is the near surface resolution?
Okay, so if we're talking about resolution in terms of spatial resolution, time resolution would be a different issue. But with spatial resolution, with the membrane that we're using, obviously it's going to be a function of the type of transducer that we use and the frequencies that we use to get improved resolution. And so we've used these membranes up to 10 megahertz, so that would improve resolution. We can go with maybe thinner materials that would improve resolution. But one of the things I think that can really improve the resolution of this technique is if we use a delay line, where now we can perhaps focus the ultrasonic waveform to the surface, and that would improve our resolution. So that would improve it and still use the solid couplet material. And what was the second part of that question?
The second part was related to the near surface resolution.
Okay, that's correct. Yeah. So addressing that second part of the question, it would be using a delay line, using the solid couplet material. We feel like we can focus the waveform and perhaps get better resolution that way. So there might be some issues using the solid coupling that we'd have to study perhaps even further.
All right. Our next question is, how much pressure are you applying to the surface being tested when the probe is vibrating?
Okay, so the actuator voltage is about 2.5 volts applied to the linear voice coil motor. So that equates to about 400 milliwatts of power that is applied to the actuator. So the actuator continuously can supply about 8 ounces of force at full power, and I think full power is about 2 watts And if it's intermittent, it's more. So the applied force, when you use intermittent power, can be greater than that. So if we look at the amount of power that we're applying now, based on those ratings, that perhaps we would be applying maybe a quarter of the force, and so therefore I would feel like the amount of force that we're applying, the voltages that we're using, would be on the order of about, I would guess, maybe 2-3 ounces of intermittent force. So it's the amount of force like you would have in vibration of your cell phone vibrating in your pocket, about that amount of force, and so that would be an approximation there.
A related question, Joe: does the impedance change with applied pressure?
Yes, the impedance does change with the applied pressure, and that's how that you're able to get the coupling into the material, because the applied pressure will compress the solid coupling material, and so that would change the impedance. So you would want that. You would want the impedance to change, and that's the mechanism as to how you're able to couple the ultrasonic energy from the transducer through the solid coupling medium into the part. The key here is to be able to do it repeated with the same amount of force, so you get the repeatable A scans. So that's the key there.
All right. I believe we have time for one more question. Our last question is, how would this differ, and what benefits would it have over a dry coupled wheel?
So this technique compared to a dry coupled wheel, a dry coupled wheel would be mounted on an axis, so we would be able to go in one direction, whereas where you have the transducer that is vibrating up and down, it can go in any direction, XY direction. Now, I have seen some technologies out there where you have like a ball, and the transducer's in a ball containment, and so the ball can roll around in any direction on the surface. One of the issues that you have with a ball or a wheel transducer is that you have the ultrasonic transducer within that ball or wheel, and so you might have a coupling issue, or depending on how you design it, you might have a coupling issue, or you might have a wire issue where you have the electrical wires that need to stay in contact with the transducer, and so the movement of the wheel or the ball would make it more complicated. Now, there's technologies out there that have overcome this, but it just makes things more complicated, in my opinion, that you have wires that have to be connected when you're moving something, rotating something in one direction. There might be some ways around that with different designs, but we feel like, with a ball or a wheel, it just would make things more complicated.
Thank you, Joe. We are out of time for today's session. However, if we did not answer your questions today, or if additional questions come up, please feel free to contact us. I will also mention that the floating ultrasonic transducer is available for licensing from NASA, and we'd be happy to engage in discussions offline with anyone who might be interested in licensing and commercializing the technology. We can be reached through NASA Langley's Technology Gateway, and there's a link to this website on the slide you're seeing right now. And at the end of the webinar, you'll also be directed to that website. This concludes our session for today. Thanks, everyone, for attending the Floating Ultrasonic Transducer webinar, and thanks to our speaker, Joe Zalameda, for informing us about a very interesting technology coming out of NASA.